Okay, so the first thing we're going to do today is we're going to talk a little bit about games with more than 2 strategies. And the context that I want to put this in is to pick up the context from our last meeting on Tuesday, which is that I'm showing you a set of related techniques for solving simultaneous games. Okay, the easiest technique is to look for dominant strategies. If you can solve a game by finding a dominant strategy for each player, you're done. That's it. That's great. That's the easiest way to do it. We saw at the end of class on Tuesday, though, that not all games have dominant strategies. Okay, so in the last version of the roommate game that we looked at, we saw a case where one player had a dominant strategy, the other one didn't, and there we had to do a little more reasoning to solve the game. And the reasoning was just, well, the player that has the dominant strategy will play it, the other player will play her best response to that strategy. Okay, so we're now going to keep pushing at that boundary to cases where in games with more than 2 strategies, there may be no dominant strategies, but there will be dominated strategies. I'll go into the details on that in a minute. Okay, and so that's going to be a slightly broader set of simultaneous games that we can look at by eliminating dominated strategies, but it's still going to leave us with a set of games that we won't be able to solve using the dominance relationship. Okay, so what we're going to be doing by the end of class today is solving games, looking for Nash equilibria in games where neither player has a dominant or a dominated strategy. That's where we're going. First, let's pick up this issue of dominated versus dominant. In the games that I was talking about on Tuesday, each player just had 2 strategies. So if one was a dominant strategy, if one was a better choice for the player, no matter what the other player did, the other strategy had to be dominated. Okay, the other strategy had to be not the best choice, no matter what the other player did. When you have a game with more than 2 strategies, it is possible that there'll be no dominant strategy, no strategy that is always your best choice, no matter what the other players are doing, but that you might have a dominated strategy, a strategy that is never your best choice, no matter what the other players do. Okay, so our reasoning here is going to be, if you have a dominated strategy, a strategy that no matter what your opponent does is not going to be the thing you want to do, it's not going to be the best response, we don't think players are going to play they're dominated strategies. So what I'm going to show you in a minute with an example is a way to solve a game through what's called iterated dominance, and a more friendly, clear way to express the idea of iterated dominance is that we are just going to solve the game by eliminating dominated strategies. Okay? All right, so I think that's going to be easier to see in context. Okay, so this game is a game, it's about competition in a market. It's the story in this game is we've got two companies selling pizzas, okay? What each company is trying to do is to get the most profit, and that's an important part of the game. The profit that they make depends both on the price they charge and how many pizzas they sell. How many pizzas they sell is also affected by the price. Okay, so price kind of has both a direct and an indirect effect. Here, if I sell at a higher price, the higher revenue is going to increase my profit, but if my price is higher than my competitors, some of my customers are going to go to the competitor. Okay, so we're going to set that up in a game. This game is going to take a little bit of effort to set up. You guys are used to that now, that a lot of the hard work in sequential games was actually in setting up the tree. That's going to be true in setting up the matrix here. Okay. So what we've got with pizza companies, I think I gave them interesting names like Pizza Company A and B. They both basically face the same situation. Okay. I'm going to make a little table here for price and profit per pizza. Okay? If they charge a high price, I'm not even saying what it is, the profit per pizza is going to be 12. Okay? That's pretty good. I want to be in this business. Doesn't sound like the real restaurant business to me, but this is the numbers that I have. A medium price is going to give them a profit per pizza of 10, and a low price, a profit per pizza of 5. Okay. So here's the price and profit story. The other thing we need to know is, what is the demand for pizzas? Okay. How many pizzas are people going to buy? All right. And the demand here, we're going to think about this per week. Okay. Each company, has 3,000 loyal customers. O-M-E-R-S. Okay? So loyal customers, what does it mean to be a loyal customer? It means they like my pizza. Okay? If I'm Pizza A, they're not buying from Pizza B. No matter how high my price is, they are loyal. They like how I do it. They're not going to buy from Pizza Company B. But there's also 4,000 floating customers. These are all college students. They're going to buy from the cheapest company. Okay. Maybe you guys aren't like that. Maybe you have more sensitive palates. But when I was in college, and actually long since, I've been kind of a floating customer. Pizza's pizza. I want it to be cheap. They will buy from the cheaper company. Okay. So what makes this a strategic situation now is that if I'm Pizza A, my profit depends on my price, okay, but it also, through the floating customers, depends on my competitors' price. What I'd really like to do is have my price as high as possible, but the problem is, if I have my price as high as possible, my competitor might come in and take all the floating demanders, and 4,000, that's a lot of people. I'd like to be selling those pizzas to them. Okay. So what I'm going to do is I am going to I think over here, do a preliminary step. Is that how I want to do it? Actually, I don't. What I want to do, I'm not changing my mind about how I'm going to use the board. I'm going to have my main game here. I'm going to start to set it up first. Okay? Then I'll go over here and do a little bit of extra calculation. All right. So this is a simultaneous game. And this, more than the examples I was doing on Tuesday, I think really is a simultaneous thing. The pizza companies say they print out their menus, do their flyers simultaneously when I'm doing my promotion for this week where I'm letting my customers know what my price is. I don't know what my competitor's going to do, and vice versa. Okay? So we're going to have me, Pizza A, be the row player, and you guys, Pizza Company B, be the column player. And now in this game, each of us has 3 strategies. The choice we make is what kind of price we charge, high, medium, or low. Okay? So here, my game matrix now needs to be 3 by 3 instead of 2 by 2. Okay? Because there's 9 possible things that can happen. Depends on my price and your price. Okay? So we can both choose high. We can both choose medium. We can both choose low, and there can be any other combination. I choose medium, you choose high. I choose medium, you choose low. All the cells are pictured here. Okay. In this game, this is the game matrix. The cells will contain payoffs. Okay? In this game, the payoffs are all about profit. Okay? This is a game that's all about profit. Okay? But to calculate the total profit, I need to figure out how many pizzas each company is going to sell in each of these combinations of pricing schemes. Okay? And to do that, what I'm going to do over on this board in blue is not the game. Okay? Just a step, though. I'm going to do that same matrix, or not the profit game. And what I'm going to do here in the cells is not have the payoffs, but the cells show the number of pizzas sold. Okay? So I'm doing this self-consciously as an example. When you have a simultaneous game where the relationship between the strategies, the outcomes, and the payoffs is complicated, sometimes you want to make yourself a separate matrix that doesn't have the payoffs in it but has some intermediate step. Okay, so this is like the simultaneous version of writing the outcomes above the payoffs before the terminal nodes in a game tree. Okay, so this is number of pizzas here. Depends on my price, depends on your price. Okay, so one thing that can happen is we can set the same prices. We can both do high, we can both do medium, we can both do low. Now I didn't actually say over here what the floating customers do then. I'm going to tell you now. Okay? They split evenly if the prices are the same. Okay? So I'm Pizza Company A. I'm setting a high price. You guys are setting a low price. How many pizzas do I sell during the week? I sell 3,000. I actually sell a few more. Okay? I sell 3,000 to my loyal customers. Am I getting any of the floating customers? I'm getting 2,000. Okay, so I'm getting 5 here, and you guys are getting 5 too. Okay, and because we're just doing the number of pizzas here, price doesn't matter. The 5s are going to be true in all 3 cases where we set the same price. Okay, these floating customers aren't paying attention to absolute price. They're not saying, well, we're not buying if the price is high. They're just buying from whoever sets the lower price. Okay, so they're going to get their pizza no matter what. Okay, what about here? I set a medium price and you set a high price. How many total pizzas? I get 7,000. Okay, now my price is lower than yours. All the floaters go to me. That's good. How many do you sell? They have to really love your pizza to buy from you when you're charging the high price and I've got the medium price. Same story here with the low price, right? If I'm setting the low price and you're setting the high price, I'm getting all the floating demand, plus I'm getting my loyal customers. You're only getting your loyal customers. And it's true here too. If I set a low price and you set a medium one, my price is still lower. Okay? All they're reacting to is which one is lower. All the floaters go to me. You only have your loyal customers. And in these 3 cells, the roles are reversed, but it's the same basic pattern. In these 3 cells, now you guys, Pizza B, you're setting a medium price. I'm charging a high price. All the floaters go to you. You get 7, I get 3, and the same story in all these cells. Okay. So this is our little helper matrix that's going to now help us figure out what the real payoffs are. Okay? Neither one of us care about selling pizza per se. We're in this business to make some money, and we want to make as much as we can. All right. So now what we have to do, given that we know how many pizzas are going to be sold in each of the scenarios, is we have to calculate the profits. Okay? So let's just go ahead and do that. In the upper square, where we're both charging the high prices, we're both selling 5,000, so our profit is 12 per pizza times 5,000 pizzas. Sounds like a profit of 60,000. Profit of 60,000 a week. Like I said, this is not a realistic example number-wise, but makes it fun to think about these big numbers. In the medium cell, we're both still selling 5,000 pizzas, okay? But now our per pizza profit is 10, so profits of 50 all along here, and 25 here. I'm putting the profits in thousands here, okay? So in both cases, it's 5,000 pizzas each times the per pizza profit. 60 for a high price, 50, 5,000 times 10 for the medium price, and 5 times 5, 25 for the low price. Okay? So now filling out the other cells, here I'm charging a medium price. Okay? I'm making $10 per pizza, but now I'm selling a lot. Okay? I'm selling 7,000 pizzas here, so I've got my 70 there. 7,000 pizzas times $10 per pizza. Down here, I'm still selling 7,000 pizza, but per pizza profit is only 35. Okay. And in this cell, I'm just doing my payoffs now. We'll fill in Pizza B's payoffs in a minute. This cell, from my point of view, is no different than this one. Okay? The only thing that's different here is whether my competitor is really trying to gouge them with a high price or just setting the medium price. Either way, my price is low. I'm getting all the floaters. I'm getting 5,000 per pizza, selling 70. I'm getting 5 per pizza, selling 70, 3,000, there's the 35 here. Okay. So what are you getting in these cells? Here, you're selling 3,000 pizzas just to your loyal customers, but because you are setting the high price. Okay. Now we're looking at the column players, number of pizzas. The column player strategy is a high price. 3,000 pizzas times 12 per pizza is a payoff of 36. Right? Okay. 12 times 3,000. And down here, it's the same story, okay? The only difference here is in Pizza A's strategy. From the column player's point of view, here the column player is still selling to all 3,000 loyal customers at the high price per pizza profit of 36 here. Okay. What else can happen here? The only other thing that's not going to be a mirror image here is what happens when Pizza B sets a medium price and Pizza A sets a low price. The medium price gives me a profit of 10 per pizza, and I'm selling 3,000, so I'm getting 30,000 profit there. Okay. Okay. So I've filled in this part of the matrix. This game is one that's symmetric. You guys will remember from Tuesday, games don't have to be symmetric. Sometimes one player's payoffs can be systematically different from the other, but this game, like the Prisoner's Dilemma, the two players really want the same thing, face the same incentives, so the outcome here, when A sets a high price and B sets a medium price, is just the reverse of what happens when A sets medium and B sets high. Okay, so A doing the high price, 3,000 pizzas at 12 per pizza gives me 36. This is 70, and I'm just going to go ahead and reflect the payoffs here. But while I'm doing it, I'm going to keep the story going in my head, because a very important thing in both setting up and solving simultaneous games is to get the numbers in the right places. Okay, so I've got to make sure here that I am accurately putting the numbers in the right place. Okay, so 36 is the profit that you get from setting high when your competitor sets low. It's the column player's profit in this square. It's the row player's profit in that square. The profit you get from setting low when your opponent sets high is the column player's profit here. There's the 35. Okay, when I set medium and my opponent sets low, that is the same thing as when I set low and he set medium. That is the 30. And from his point of view, it's the same as when I set low and he set medium. Okay? All right. So just as with sequential games, the setting up, a lot of the work goes into the setting up. Okay? And especially this mapping from the combinations of strategies to how that affects what happens to the thing that we care about, that can have a lot of steps. And the finished game won't show all the intermediate steps, but it's a good idea to do those intermediate steps on a sheet of paper so that if something weird happens, you can go back and check your work, see if it all makes sense, help you reproduce the argument. Okay, so here's my game, and let's kind of go through the algorithm that I was developing on Tuesday. Let's look to see if anybody has a dominant strategy. Okay, well, I'm just going to start up here, and I'm going to look at it from the row player's point of view. Okay, well, high is definitely not a dominant strategy because right away here we see that player A does better setting a medium price when the opponent sets high. So maybe medium's the dominant strategy. Medium's a better choice when your opponent sets a high price. Medium's a better choice when your opponent sets a medium price. Oh, look here. When your opponent sets a low price, though, high is actually better. Okay, so medium's not a dominant strategy either. For it to be a dominant strategy, this row would have to have the highest number in every column. Okay, it's got the highest number in this column, the highest number in that column, but not the highest number in this one. Okay, so not a dominant strategy. Low, also not a dominant strategy. Okay, so no single strategy gives the highest payoff in all columns or in all rows. Okay, we could do it from the background, but next we'll look for dominated. Reza. Medium is always better than low, and that is right. That's germane to the next point that I'm making. It doesn't make it a dominant strategy. Okay? And this is the thing that was the same on Tuesday. On Tuesday, if one strategy dominated the other, the dominating one was the dominant strategy because there were only two. Now, it's possible for medium to always be better than low. In fact, it's absolutely true that it is. But medium is sometimes a worse choice than high. Okay? So medium dominates low, and so does high. High also always gives a higher payoff than low. Okay? So what we have here is we have no single good strategy that we can just say, oh, that's what they're going to go with. They're always going to go with medium, because there is actually a case where you could be sorry you went with medium. If your competitor sets a low price and you're not going to get any of the floaters anyway, you're going to wish you had more profit. So you're going to wish you had done high. What we can say, though, is that low is never the best choice. Low is never a good choice. No matter what the other company does, you don't want to set a low price. Okay? It's never going to be the best thing. If you set a low price here, you're settling for 35 when you could have had 60 or 70. Here, you're settling for 35 where you could have had 50 or 36. I mean, granted, it's just one more, but on the other hand, we're counting in thousands, right? You'd rather have the 36. Here, you're settling for 25 when you could have had 30 or 36. Okay? So low is a dominated strategy. In this case, it is dominated by both of the other strategies, but all it would have to do is be dominated by one for us to say we're not going to play it. Okay? So that's what we're going to say, and look how I'm going to do this. I'm just going to cross it off. Okay? I'm doing what I said I was going to do. I'm going to solve the game by crossing out, by eliminating dominated strategies. I'm not setting a low price. It's never a good idea. Okay? Guess what? You look at it from the same way, never a good idea for you either. Yeah?
So you say that if only one strategy dominates another, then that's easier to say that it's a dominant strategy?
Yes. It doesn't have to be both. It doesn't have to be both. Let me just really re-emphasize that. If it was just medium that was always better than low, you could kind of go through the reasoning. You would never play low. Okay, medium would always be a better choice, so it's like low just isn't relevant. Okay? And from the point of view of Pizza B, trying to strategize, wondering what I'm going to do as Pizza A, Pizza B is going to say, well, she's smart enough to know that low is never a good choice. I don't have to worry about her playing it. Okay, so we're going to take this dominated strategy out of the game for A, and we're going to take it out of the game for B, And then we're going to iterate. Iterate just means repeat. Okay, now we've got this smaller 2 by 2 half-solved game. We're not paying attention to this row or this column. We've eliminated them. Looking there, now in this smaller 2 by 2 game, is there a dominant strategy? Medium is a dominant strategy now. Okay? With the dominated strategy removed, now medium is always best. Medium is the dominant strategy for both. Okay? The other way you could think about this is you could think about it purely in terms of dominated strategies. Okay? Now in the smaller 2 by 2 game with the low row and the low column eliminated, now in the smaller game, medium dominates high. High is dominated, so we cross it out here for the row player. We cross it out here for the column player. This is what we are left with. Okay? So this is our prediction, and we got here by eliminating dominated strategies, by iterated dominance. Okay, so that's pretty good. Sometimes we can do that. But I've already set you up for this. We're not going to be able to do it all the time. And what I'm going to do is I'm going to start erasing from the outside in. While I'm erasing, think about if you have any questions about this 3-strategy game, because if you don't, I'm going to go back to variations on the prisoner's dilemmas that we were working on last time. So Elaine's asking, is this sort of a general algorithm? Okay, look for dominant strategies. If there aren't dominant strategies, look for dominated strategies, cross out the dominated strategies, and then look at the smaller game, repeat the same process. Yes, that is a pattern that you can use. It's not a pattern that's going to work every time. It'll work for a few games that you can't solve with just dominant strategies, but whenever it works, it's always going to get you valid prediction. Okay? And the logic is pretty transparent. If we think somebody has a dominated strategy, it's never their best choice, and we're trying to out-strategize them, we're going to say, okay, they're as smart as me, they're never going to play their bad choice strategy, and lo and behold, that simplifies my problem. Okay? And both of the pizza companies are going through that logic here. Okay. So what we're going to go back to now is the room cleaning story that we had 2 variations of that I'm going to flash through real fast here, and then we're going to go to a new variation. Okay. So we've got roommate A and roommate B, strategies being leave your mess, clean your room, leave your mess, clean your room. And the very first set of payoffs we had, I'm just copying them right back in from what we had on Tuesday. This set of payoffs made the game a prisoner's dilemma. It made the game a prisoner's dilemma. Just recall what we were doing at the end of class on Tuesday, because the payoffs fit that prisoner's dilemma pattern. There is a temptation payoff, which is the highest one. It's larger than the reward payoff that the players could get if they both did the socially optimal thing. The reward payoff is higher than the punishment payoff, which is what we think that they're going to get, and the punishment payoff is higher than the sucker payoff. Okay, so the problem with the prisoner's dilemma is these extreme values here when one player does the socially optimal thing and the other one does not. Okay, the other way to say that, these extreme players, when one player plays their dominant strategy and the other one doesn't. When that happens, the player that played the dominant strategy gets this tempting payoff. They really hit the jackpot, and the one that didn't play the dominant strategy gets the sucker payoff. Okay? That is what drives us to end up at this inferior cell where we both play our dominant strategies, even though we'd both rather be here. Okay. So still reviewing, I don't think I'll use color here. I think I'll just erase. What we did on Tuesday was we thought about what happens when one player's payoffs don't fit the prisoner's dilemma story. Okay, we didn't call it iterated dominance then, but actually that was the process that we were using when we have the column player having a payoff here that is lower than this one. Okay, so what this means is, from the column player's point of view, if her roommate cleans up, she prefers to have cleaned up too. Okay, so she gets a higher payoff in this row from cleaning up than she does from leaving a mess. So this is B with a conscience here. In solving this game, we still use dominant strategies. Okay, we basically said B doesn't have a dominant strategy, but A does. A is not going to play her dominated strategy, okay, so that would be in effect eliminating this row, being left with a smaller game for B, and in this smaller game with just one row, B plays her best response here. Okay, so iterated dominance. All right. And same unhappy story. Just changing one roommate's preference wasn't enough. Okay. Now I'm going to change them both. Okay, and this really does change the game. It changes the game from something that we can solve with iterated dominance to one where we just have to look for Nash equilibrium, and that's what we're going to do now. Okay? So what I've done now is I've changed both roommates' preferences so they both kind of have this conscience happening. Both of them prefer to clean up, okay? Column player here, row player here, when their roommate has cleaned up. If their roommate's left a mess, they're not that sweet, okay? If we're in this column, B has left a mess, I'm A, I'd rather leave a mess too, okay? I'm not going to be a sucker, okay? But I don't have that temptation anymore. That's what we've changed here, okay? In this game, this is a happier game, okay? Look at this cell. Look at the cell, the 3-3 cell, the reward cell. Okay? Say we're here. If we are here, the question to ask is, does either player have regrets? Okay? Given that B cleaned up, is A sorry she cleaned up? No, A's glad she did. A's glad to have the 3 rather than the 2. And given that A cleaned up, B's glad she did too. She'd rather have the 3 than the 2 here. Okay? When the answer is no, that means these strategies, this row and this column, form a Nash equilibrium. Okay? I've said a couple of times throughout the class that the idea of Nash equilibrium is really the same as the rollback example. It was actually developed in the context of simultaneous games. And I guess that's why we use Nash's name more in that context. It's not wrong to call a rollback equilibrium a Nash equilibrium. But let me just put the definition of Nash equilibrium up here, and you're going to recognize it. It looks pretty much like the roll back. 1. Okay. Nash equilibrium is a set of strategies, one for each player, sounds like rollback, right? Such that no player can improve their payoff by deviating from the strategy given the other players' strategies. Okay. So our strategies are in equilibrium if given what you did, I can't do better by changing what I did, and given what I did, you can't do better by changing what you did. Okay, so to repeat from Tuesday, the phrases that should come to your mind that you should associate with Nash equilibrium, one is this idea that we're playing best responses to the other. Given what you did, my choice was a best response. Given what I did, your choice was a best response. Our choices are self-reinforcing. Nobody has regrets. Okay? So this cell is indeed a Nash equilibrium. And how are we finding it? Okay? We're not eliminating dominant strategies, or not eliminating dominated strategies. We're not picking dominant strategies because there aren't any in this game. What we are doing is we're just looking at each cell and asking ourselves if it's a Nash equilibrium, or at least we're in the process of doing that. Okay? That process, Dixit and Skeeth call it cell by cell inspection, and that's about what it is. We're just going to look at each cell and ask ourselves, if we find ourselves doing this, are we in equilibrium or does one of us have regrets? If neither of us have regrets, then it's a Nash equilibrium. If, given what the row player did, the column player couldn't have improved her payoff. Given what the column player did, the row player couldn't have improved her payoff. That's an equilibrium. Okay? So that's a happy story. Now the apartment's clean. Okay? All I had to do was get rid of that temptation, and now if we both clean, we're both happy. But there's always a but. It's not the only Nash equilibrium. Okay? And this is something that we didn't have to deal with in sequential, in the sequential games we covered. Okay? There's another Nash equilibrium. Look up here. If we're in this cell, if you left a mess, you're the column player. I, the row player, I am glad I left a mess too because I don't like feeling like a sucker. And given that I left a mess, you're glad that you did too because you don't like feeling like a sucker either. Look at this. Here's another Nash equilibrium up here. Okay? So this game has two Nash equilibria. There are two combinations of strategies that are self-reinforcing, that are best responses to each other, that will leave both players without regrets. Okay? And game theory cannot tell us which one of these is more likely to happen. Okay? Game theory could tell us that this is not an equilibrium. Okay? If this happens to me, I'm the row player, I'm going to change. I don't like this outcome. If this happens to you, you're the column player, you're going to change. You don't like feeling like a sucker either. Either of these patterns can be self-reinforcing, and to arrive at a prediction of at which one would happen, we're going to have to go outside of game theory. Okay? We're going to have to think about what the players expect of each other. We're going to have to think about what they've done in the past, what kind of culture they're like, what their history is like. So this point where we have to confront the fact that there could be more than one Nash equilibrium in a game is the point where the kind of abstract, mathematically oriented game theory really hooks up with historical, anthropological kinds of knowledge that let us know in a particular context which one of the two equilibria can be more salient. In these situations where there's more than one equilibrium, we think that things like communication and leadership are very important. Okay? After class, was it Lillian was talking to me about the prisoner's dilemma scenario, and she was asking, she was bothered by the, right? You were bothered by, I just couldn't find you for a minute, by this extreme inefficiency here, okay? And made the very good observation that if these guys are roommates, couldn't they just like explain we'd both be happier if we'd have a clean apartment? That kind of explanation would be much more likely to work and to be reinforcing if it was in a situation where we weren't being confronted with the temptation here, okay? So games like this that are sort of like the prisoner's dilemma, except that there's this other equilibrium, are games where, as I said before, communication and leadership can make a huge difference in taking us from a bad equilibrium to a good equilibrium. This kind of game is so important, its relationship to the prisoner's dilemma is so important that it actually has more than one name. Most often, this game is called an assurance game. Okay. I guess the idea is that if you're assured that your partner is going to be playing the strategy that goes with the good equilibrium, you want to do it too. Another term that you will hear is stag hunt, which I think is from the writings of Rousseau, some kind of great Enlightenment thinker, even before game theory was invented, put his finger on this problem that in this case, if we're hunting a stag, there's lots of incentives to all go off our own way and try and get the stag for ourselves, but guess what? It's probably not going to work out. It takes a bunch of people to bring down a stag. We're all better off if we work together. Okay, so stag hunt is another name for this game. Okay. Okay. So some of the most interesting applications of game theory to historical events have involved looking at this assurance game. I just said a minute ago that if you're in this game, that having a leader, someone who will stand up and say, hey, everybody, we expect to be here. This is the equilibrium we all want to be at. Let's do it. We'll all be better off. Those words will be meaningful in the context when, if we all get there, we'll be glad we're there. Okay? It'll sound more like empty rhetoric if we think, oh, when we all get there, we're all going to be looking for some way to cheat, and it's probably going to fall apart right away. Okay? There's a famous book about the civil rights movement by Dennis Chong. It's called Collective Action in the Civil Rights Movement. And it goes through kind of the history of the civil rights movement as it developed in the South. And he especially focuses on the role of black leaders in the churches. And basically what he says they did, they weren't thinking in terms of an insurance game, they were just thinking in terms of solving a problem of getting people to participate in marches and sit-ins and things like that, even when there was a pretty strong incentive to stay home. The incentives were pretty strong in those days. You could get beaten up, jailed, even lynched for participating. But what they were able to do was to turn some of these protest events into something that if everybody you knew, all the people in your community were part of the protest, you wanted to be there too. You wanted to be part of it. People would notice you were missing. People would think well of you if you were there. They would think you were a cheater if you weren't there or that you weren't part of this historic movement. And that is, I think, maybe what Lillian was thinking of with the roommate. That's a case of leaders first changing preferences. Okay, first changing preferences so we have the assurance game, not the prisoner's dilemma, and then second, making sure that everybody knows that this is the equilibrium we want to be at. Okay, that everybody understands this. And leaders in all sorts of cases, in Congress, in companies, in academia, are people who are able to let the followers know that they're in this situation. Hey, followers, if everybody else is participating in this good thing happening, you want to be there too. You want the 3. If you're the one who stays home and does what seems to be the thing in your own self-interest, you're going to be sorry. Okay, that kind of communication is really, really helpful. And at the same time, I don't know if this will ring true to you. A lot of the people I know who are good leaders are embarrassingly optimistic. Really, it's going to work. It's going to happen. Really, rah, rah, rah. How can they be that way? That rah, rah rhetoric is telling everybody this is the equilibrium we're going to be at. Okay? So it can be really, really very useful. An example from my life where that hasn't worked out so well was last year there was a fundraiser at my kids' school, and I'm sure you guys remember these kind of things, whether you went to public or private schools. Schools are always raising funds, and they're always trying to get as much participation as possible. And this is an example of what I would consider bad leadership strategy. The mom who was running some kind of silent auction night tried to use the guilt strategy. Look, nobody's helping me with this. The whole thing's not going to work. Okay, and it didn't work. Okay, what tends to help is, look, everybody's participating. You want to be at the silent auction? We're all going to do it. Her rhetoric of, hey, I really, really need your help. We've only sold 5 tickets. The whole thing's not going to happen. What that did was that let everybody know we're at this equilibrium. Okay, we could be at the good equilibrium, but we're actually at the equilibrium where nobody's going to show up. Okay, so you guys, UCLA students, many of you are current and future leaders. Maybe that's something to think about there. Maybe I'm telling you something you already know. Okay. Okay, I want to say one more thing about this issue of multiple equilibria in one game. And what I want to do is I want to distinguish multiple equilibria in a single game from the kind of thing we were doing before the midterm, where we would have variable payoffs and there would be more than one case of equilibria in the set of games that were represented with a variable payoff. Okay, so what I'm going to do now is I'm going to make this payoff a variable. We'll call it T for temptation. Okay, so now we're in the world of variables and payoffs, and in thinking about what's going to happen, we're probably going to have cases, right? Okay. So in asking ourselves, if we start down the path of looking for dominant strategies, we ask ourselves now in this game where T can be any number, T can be a variable, we ask ourselves, is there a dominant strategy? Well, the answer is going to be it depends on how big T is, and there's going to be 2 cases. Okay. Okay. So either from the row player's perspective or the column player's perspective, what matters is whether T is bigger than or less than 3. We're going to continue to ignore the knife edge cases here. Okay, so one case is T is greater than 3. T is greater than 3. Is there a dominant strategy? Yes. Okay. T is greater than 3. The game's a prisoner's dilemma, right? T is greater than 3. I'm A. I'd rather leave the mess when you clean up, and I'd rather leave the mess when leave the mass. In this case, the only Nash equilibrium is mass-mass. Okay? Second case, T less than 3. Dominant strategy now? No, right? This is the case we were just looking at. If T is less than 3, it's the assurance game. If T is less than 3, then what I want to do depends on what you're going to do. Okay? If T is less than 3 and you clean up, I'd rather clean up too. Okay? But if you leave a mess, I'd rather leave a mess. In this case, there are 2 Nash equilibria. For T less than 3, both clean as an equilibrium and both leave a mess as an equilibrium. And mess. I picked 3 because that's the comparison we're making. And actually, let me highlight that since that's really the important thing that you need to be able to do. Okay? In asking myself whether there was a dominant strategy, okay, I know that 1 is greater than 0. Okay? No worries here, no variables. So I know that if we're in this column, I want to be in the mess row. The question is if we're in the clean column. Okay? Then the question here is whether T is greater than or equal to 3, or is greater than 3 or less than 3. Okay? When T is greater than 3, then mess is the better choice no matter what the roommate does. Okay? So just as in sequential games, the cut points, the values of the variable divided into cases, we get that from solving the game. Okay? We got it here by comparing the row player's payoff from what she gets from leaving a mess when her roommate cleans to what she gets from cleaning when her roommate cleans. Okay? And figuring out which one was higher, 3 was the critical value. The point I wanted to emphasize here, though, is that this is what we mean when we say multiple equilibria. Case 2. Is a case where there's more than one Nash equilibrium. Okay? This is a game where we would say there's a single Nash equilibrium. Sometimes people use the word unique here. So multiple equilibria is not the same thing as the kind of cases that we get when there's a family of games that have different equilibria depending on different parameter values. All of those sequential games where we had multiple cases, 3 cases, I can't remember if we actually did one with 4 cases, but however many cases you have in those kind of sequential games, in any given case, once we know the values of the variable, there is only one rollback. Here we have something weirder happening. Here we have, yes, what happens depends on the values of the variable, but here even for a very specific value of the variable, the value I had 2, for example, there's more than one equilibrium. Okay? So that's stranger, and it can be a little bit less satisfying. I mean, so far, yes, we've had to make a lot of assumptions, we've had to simplify our scenarios a lot, but we've been getting very clear predictions about what we think people are going to do. Here, no, not in the case where there's more than one Nash equilibrium. Okay? We can rule out some things that we don't think are equilibria, but game theory alone can't tell us which one is more focal. Okay, I think I'll even put that word up. Okay? When there's multiple equilibria and we ask which equilibrium will occur, well, I said the answer doesn't come from game theory. The answer comes from outside game theory, but game theory at least has a name for it. We just say sometimes one or another is focal. Okay? Whatever one people think will happen, will happen. things that go into making one equilibrium or another one focal are what's happened before, what the players think is normal, what happens in similar situations. That sort of drives you to think about the culture that the players come from. But these are all things that are outside the world of strategy, okay? Things that establish focality. Sometimes you might look at this game and say, doesn't the fact that this equilibrium is better for both players by itself make it focal? You kind of think that it should, right? And sometimes that's true. So I've sort of said a couple of times, the argument that both cleaning is better than both players you think might actually be persuasive here. But you could think of cases where one equilibrium is Pareto dominated by the other one, and yet this one persists. The most famous case is called the hockey helmets case, and these days hockey players all wear helmets, but at the time people were sorting this out, professional hockey players and most amateurs too didn't like to wear helmets, okay? It hurts your vision. You really see much better if you don't have that big thing around your head. And people were pretty much, so they were all at this equilibrium where nobody was wearing helmets and a lot of very serious head injuries happening in hockey, very fast sport, hard pucks, okay? Eventually, the leagues, both professional and amateur, created rules to force people to wear helmets, okay, so that now this is the focal equilibrium, and I don't think players really want to go back to it. Hockey players are tough human beings, but I think they're willing to mostly wear those helmets. Fact is, though, for years and years, hockey was played without helmets there. They really were at the equilibrium that was Pareto dominated. Okay. I've heard people make a similar argument about drug testing these days in sports, like in the Tour de France and other sports, where maybe all the players would really like to be at the equilibrium where nobody's doping, but maybe not. Okay, the only sport in that category that I follow is cycling. In my sense, is that cycling, the problem is that it really is a prisoner's dilemma, that those guys really do want to win so much that they'll happily take anything their trainer tells them to. Okay. One last game to look at, and it's going to sort of tie up the discussion of focal points. Seems like a good game to work in on Valentine's Day, is the Battle of the Sexes game. Okay, so this is another classic game. These games that have names usually achieve that status by being metaphors for situations that occur over and over again. So what's Battle of the Sexes? Battle of the Sexes, the players are a guy and a girl. Okay. So him and her. In this game, we're going to let her control the rows, and him is going to get to choose the columns. And both of these guys are making a choice simultaneously. Okay, they're not allowed to talk to each other, and no one can move first about where they're going to go. And there are two choices. They can go to the ballet, or they can go to the ball game. Okay. They can. And getting sort of skirting the edges of being politically incorrect here, but well, honestly, I'm not a huge fan of ballet, but ball games, please. I'd rather go to the ballet, and yeah, I think my husband's not a particularly macho guy. I don't think he really likes ball games all that much, but he sure doesn't want to go to the ballet, and I think there's a pattern there. The girl would like to go to the ballet. The guy would like to go to the ball game, but they like each other. They'd really like to be together. Okay? So here are the payoffs. If we both end up at the ballet, from the girl's point of view, I like that. That's my high payoff of 2. The guy's like, okay, I'm not really into this, but I like sitting with her. She's happy. This is good. He's liking that. From the other point of view, if they both end up at the ball game, the guy's like, oh yeah, I like this. And the girl is, well, I still think he's cute. I've got my iPod. I'm going to be okay. I'm getting one here. So those are the on-diagonal things. Those are what they want to be together. This is when people talk about coordination games. This is the story that they have in mind, the battle of the sexes. Okay, but what else can happen? Okay, well, one thing that can happen is I go to the ballet, I'm the girl, and the guy goes to the ball game, and, I'm enjoying the ballet. That's pretty good. He likes the ball game. It's kind of lonely, but we both had interesting afternoons. The worst thing is I'm the girl, I go to the ball game, I'm here by myself. It's so boring. I'm getting a sunburn. I hate it. And let's just not even talk about how the guy feels at the ballet. This is so not him. Those are really bad payoffs. Okay, so yeah, that's the Battle of the Sexes story here. So this is a game where I think it's probably pretty easy to see there are two Nash equilibria. Here's one Nash equilibrium. How do we see it? Okay, we see it because I'm the girl, I'm the role player. Given that he's at the ballet, you're darn tootin', I'm glad I'm there. If I'm the guy, the column player, given that she's at the ballet, it turns out I care more about her than I care about sports. Wow, how's that? So this is one Nash equilibrium, but so is this. Okay, again, I set it up to have this kind of symmetry. From the girl's point of view, given that he went to the ball game, I like him, so I'm glad I'm at the ball game too. And from his point of view, no question, I'm at the ball game, she's at the ball game, no regrets. Okay. What is interesting about the Battle of the Sexes, why this is probably the, I was going to say this is the game that's used the most in political science. That's not quite true. Prisoner's dilemma and insurance are used a lot too. But this is a very political game. Okay? Because this game, there are two Nash equilibria, and in contrast to assurance, when we both liked one better, here each player likes one equilibrium better than the other. Okay? So there's two Nash equilibria, and each player prefers a different one. Okay? So one of the most common applications of this Battle of the Sexes logic is primary season, where we're at right now, choosing a presidential nominee. Okay? If this is the Democrats, Clinton versus Obama, some people prefer Clinton, some people prefer Obama, but Democrats in general would prefer that we would all coordinate sooner rather than later. That's not happening so well. It's happening better on the Republican side right now, even though, interestingly, I think the divisions on the Republican side are stronger, that the people who liked Romney in particular really aren't very happy about McCain, but there's, if you've been following the op-eds since Super Tuesday, one high-profile conservative after another has kind of said, if McCain's going to be the nominee, okay, so say I'm William Crystal and I'm in the situation of the girl who's seeing that the guy's going to go to the ball game. Okay, the nominee is going to be somebody I don't want, but I'm still rather be there than have a divided party go into the general election at a disadvantage. Okay? So, yeah, I really like this game because of that feature. Okay? Game theory by itself is not going to tell us which equilibrium we're going to be at. Okay? Maybe that's a little too strong. This game by itself is not going to tell us which equilibrium we're going to be at. If you think about strategy during the primary season, there's a lot of strategizing about trying to control expectations, a lot of the rhetoric about bandwagoning and momentum and things like that. What people are trying to do by, say, asserting that their candidate has momentum is to make their preferred outcome become the more focal one. Okay? and they're both trying to do it. So that's the fun part of it. Okay, so we're good. We covered a lot of ground. Today, on Tuesday, this is I think the first time I got to the end of my outline. On Tuesday, we're going to start mixed strategies. Okay, so I'm not remembering right now what chapter that is in Dixit and Skeeth, but it's something that if you have time over the weekend, since you don't have a homework set, I would look at the chapter on mixed strategies. Okay.